This is a video to show how to solve a quantitative inclined plane problem. Now, yesterday in class, we looked at how to look at the problem qualitatively and to do the force diagram. We also talked about how to switch the axes around. So let's start there and just review a little bit so that you know what you're doing. All right, so this is a real basic inclined plane problem. We have a block on an incline, and when we draw the force diagram, we identified three forces: the weight down, the normal force perpendicular to the plane, and the friction force keeping it from sliding down the incline back up the incline. So here's our force diagram, and since it's a static equilibrium problem, since the box is stationary, those forces, when we add them together, graphically we see the vectors all combine into a closed figure, a triangle, so we know that the forces are balanced. In addition, we notice that the normal force and the friction force are at right angles to one another, and that's going to become pretty important today. All right, so, and we also have our, there we go, our axes that we could rotate around. So let's take a look and see why we want to rotate these axes. All right, here's our standard coordinate system with an x and y coordinate system. And anyway, if we were to solve the problem this one, we have the weight vector straight down on the y-axis, so it's got only a y-coordinate. But our normal force is going to have components both in the x direction and in the y direction. And the same with our friction. It's going to have components in both directions. So we can do this problem, it's possible to do, but then when we do this, we're going to have to worry about the relative sizes of these. It's going to be a little more complicated problem. Now, if we go over here and we look and we rotate our axes, so we have, in this frame of reference, we have a perpendicular plane, a perpendicular axis, and a parallel axis. Notice that the normal force is already in the perpendicular plane, the friction is in the parallel plane, and it's only the weight force that we have to worry about. So what we're going to do is we're going to then resolve the weight force into two parts, one that is perpendicular to the plane and one that is parallel. And this is a much easier problem since we only have one force to worry about resolving. And in fact, if you notice, these are all going to be balanced. This is going to balance this. This is going to balance this. It's going to be a much easier problem. So let's go back and solve this one. All right, and remember, when we're talking about the frame of reference, the block doesn't care how we look at it. We could be looking at it from this side, from the back side. We could be changing our angle, rotating it, looking from the top down. The block doesn't care. It's just going to sit there. So we're going to choose the perpendicular and parallel axes. Just like that. That'll be our new frame of reference. Let's get rid of the XY since we're not going to need that. We'll resolve the weight vector into its parallel or perpendicular and parallel components. And then just so we get the geometry right, remember with this one, we see that that's a 28-degree angle in here. And because these are at right angles, and we rotate them around 28, this also has to be a 28-degree angle. All right, now it's time to do some trig and find out the values for the perpendicular and the parallel component. So with the perpendicular side, we see that it is adjacent to the 28-degree angle. So with SOHCAHTOA, we find out that we know that if it's the adjacent side, so it's got to be cosine. So our perpendicular component is going to be just the weight vector, the hypotenuse of that triangle, times the scaling factor, the cosine of 28. And we also know that the weight is equal to mg times the cosine of 28. And when we do the trig and do the math, 13 kilogram box or block times 9.8, the gravitational field strength, times the scaling factor, we get 112.5 newtons. With the parallel component, that's opposite the 28-degree angle, so we're going to have to use sine for that, SOHCAHTOA. Okay, so we have the weight vector, the hypotenuse, times the scaling factor, the sine of 28. We know again that the weight is m times g, 13 times 9.8. We scale it with the sine, 28, and we find out that that side is 59.8. And if we look back at our diagram, which is drawn pretty accurately, this is the shorter side, this is the longer side. So these numbers make sense. That's important in these problems because it's pretty easy if you have a sloppy drawing to maybe think that this might be 28 degrees if you're not too careful drawing. So make sure that this makes sense for you when you draw a good drawing. All right, now I've set up a table over here, and we're gonna look at we'll look at these components. So we know the weight, the perpendicular component is 112.5. I've got a negative sign because it's down through the plane in the negative direction, positive away. This one, the 59.8, is in a positive direction down the plane, so I leave that positive. Now let's look at the other forces. The normal force, okay, has a component in the perpendicular plane, or the perpendicular direction, but no component in the parallel. So it's got 0 parallel component, and we don't know what that one is, so it doesn't take a rocket scientist to figure it out. The frictional force is in the parallel plane, so it has nothing in the perpendicular plane, so it's got 0 force there, and all of its force is in the parallel plane. All right, so now this is a very straightforward problem. If we look down here now, we find out, so the normal force, that's the only thing that's balancing the perpendicular component of the weight. That's got to be equal and opposite that. So this is going to be, now I've rounded using significant figures because we only had 2 significant figures on the 28-degree angle. So this one we round to 110 newtons, or 1.1 times 10 squared, and it's away from the plane in the positive direction. This one, the friction force, or actually, yeah, in the positive direction. The friction force, that's the only thing balancing the parallel component, so that one is actually going to be, because I forgot this, that's going to be a negative because it's up the incline in the negative direction, and I've rounded to 2 significant figures, so that's going to be 60, or 6.0 times 10 to the first power newtons, up the incline. So that's how to solve these inclined plane problems quantitatively. Once you do it and you rotate the axes, it becomes a pretty straightforward problem. Thanks.